thanks for the very nice introduction, especially the last part. Yeah, so today I'm going to present some work I did during my PhD. This is in class. Doesn't work. Try the. Okay, yeah. All right. So this is in collaboration with my PhD advisor, Ignacio Grossman at Carnegie Mellon. As you can see, we are both some chemical engineers that work on some optimization problems. So I want to bring you to the big context of this research. So the big question is, how do we model optimization problems under uncertainty? So it turns out this is not a uniquely defined problem. From this picture, you can see the so-called jungle of stochastic optimization. So there are multiple ways you can deal with decision-making under uncertainty. For example, you can use reinforcement learning, online learning, or stochastic programming robust optimization. This is due to William Powell, who used to be at Princeton. As you can imagine, for each of this community, you can find at least one very classical textbook. And you can imagine that you can spend your entire career on any of these communities, right? But here in this talk, I'm only going to focus on stochastic programming here, which is one of the modeling framework for modeling optimization under uncertainty. And then one of the biggest assumptions of stochastic programming is that although we do not know the value of the uncertain parameter, we do assume we know the probability distribution a priori, right? So for example, you may assume some of your parameters follow a Gaussian distribution. But what you usually do in practice is kind of take a few discrete values and then transform it to a discrete distribution. This is for computational reasons, right? Because discrete distributions are easier to solve if you have them than continuous ones. And then for each of these realizations, for example, here you have three different realizations, low, medium, and high. And each of these realizations is called a scenario in the literature. And the idea is that we will optimize the expected value over all the possible scenarios. So that's why it's usually seen as a risk neutral approach, because we are optimizing the expected value, right? And one of the common framework is called so-called two-stage stochastic programming. So let me give you some intro on what that is. So in two-stage stochastic programming, you have so-called first and second stage decisions. So the first stage decisions are the here and now decisions. Supposedly at the beginning of the time period, you take a decision X, and then you will realize the uncertain parameters. For example, in this scenario tree here, you have three different realizations with a different probability represented by tau omega 1, omega 2, and omega 3. And the H are the three different realizations. So supposedly, after you take the first stage decision, you realize the uncertainty, and then you will take some corrective action or the recourse decisions at the end. Okay. Yeah, and depending on the different realization, you can take different recourse actions. And this problem can be formulated in this closed form here. Yeah, I just want to point here. So here you have AX less than or equal to B are the constraints for your first stage decisions. And then you have some constraints for your second stage decision. For each of the realization omega, you have different constraints, right? Here in this case, we assume the first stage problems can be, first stage decisions can be mixed integer, but the second stage decisions are continuous, right? We keep this assumption for now. And then this is called the so-called deterministic equivalent of the problem. And in the objective here, you are optimizing like the first stage cost. And here in the second stage, you are optimizing an expected cost over all the second stage decisions, right? So yeah, this is a risk neutral approach. But the nice thing about this problem is that although it can be large if you have a large number of scenarios, but this problem has a very decomposable structure. So you can see that if you plot the constraints in the figure on the left, you can see that this problem is almost block diagonal, right? It's almost block decomposable. But one complicating factor is that you have to fix the first stage decisions X for those problems to be decomposable, right? So the X is called the complicating variables in this case. All right. So yeah, that's just to say if you fix X, then you can solve the problem independently. One of the algorithms to solve this type of problem is the so-called Bender's decomposition algorithms. So if you're not familiar, I will give a quick overview of what Bender's decomposition or Bender's reformulation is. So supposedly we write the problem in this form. Instead of writing problem in, explicitly, we have this function, let's call it eta omega x, that represents the second stage problem. And the definition of eta is defined here, right? So essentially, eta omega x is a linear programming problem. Pretty much, if you have the first stage decisions x, then you can solve this linear programming problem here, right? For each x, it goes into the constraints of the second stage problem. And if y is continuous, you have a linear programming problem here. Well, one of the tricks you can do is that because linear programming have strong duality, you can take the dual of the second stage problem and get the following linear programming problem. And the nice thing about this dual is that you can find the constraints is independent of x, right? The x only goes into the objective function. So therefore, in linear programming, you have the constraint is a polyhedral set. Therefore, it can be represented as a convex combination of extreme point plus the Cornish combination of extreme rays. So that's where this formulation comes from. So for the dual problem, if it is unbounded, then from LP duality, if the dual is unbounded, the primal problem is infeasible. To prevent the dual from being unbounded, you just take the finite number extreme rays and add this constraint saying that the product of your extreme rays with the objective coefficient is less than or equal to 0. But if the problem is not unbounded, the finite optimal can be achieved at one of the extreme points of this dual polyhedral. So you just take the maximum of the finite number extreme points. So with that, you can reformulate the problem as following, right? You just add these two types of constraints into this formulation, and then it can be viewed as the projection of the original problem on the first stage variables. Because in this formulation, you can see you only have the x variable, there is no y in this formulation. So this is called the Bender's reformulation of the two-stage stochastic program. But as you can imagine, if you take all the extreme rays and extreme points, there can be a large number of constraints. So therefore, the question to ask is, do we need all the extreme points and extreme rays? But the answer is obviously no, we only need those corresponding to the active constraints. So there is some ways of dynamically generating those cuts here, right? So we first consider a relaxed master problem where we only keep a subset of the extreme points and extreme rays. And then we solve the master problem and get the optimal x variable. Then you solve the Bender subproblem. And then you can generate either the so-called optimality cut corresponds to the extreme points and the feasibility cut, which correspond to an extreme ray. Then you add those cuts back into the relaxed master problem and keep iterating between the master problem and subproblem. So this is the standard Bender's framework, but it only works if you have a continuous subproblem, right? Because then the subproblem would be a linear programming problem. And then the master problem will give you a lower bound. The subproblem will give you an upper bound of the original problem. Okay, so that's some preliminary background. In the community where we call it stochastic mixed integer programming, we deal with this complication where we have mixed integer recourse in the second stage. And in this case, if you apply Bender's decomposition directly, it does not work because, I mean, you no longer have strong duality when you try to solve the subproblem, since you have some mixed integer variables here, right? So how do we make this work? What people have adopted in the literature is to say, we solve a convexified subproblem. The idea is the following. Well, in the first two constraints, it is nothing but an LP relaxation of your Bender subproblem. But we also need to add some cutting planes to convexify this set because it is a mixed integer set. But here we add some cutting planes, which is valid for this set I defined as omega because the cutting planes has to be valid for any x, not only for a particular xk. So these cuts are actually parametric for this set as omega. Well, if you go to the literature, I mean, you can find different papers. You know, there are different convexification schemes for MINLP, like Gomery cuts, lift and project cuts, RLT or CPT techniques. And for each of these convexification schemes, you can find at least one paper in stochastic MIP that use this convexification scheme in the Bender's decomposition framework, right? And the thing is that very few works has done for the nonlinear counterpart, what we call mixed integer nonlinear programming problem. The reason we want to solve this type of problem is that many applications in chemical engineering are nonlinear, right? So for this talk, I'm going to talk about stochastic mixed integer nonlinear programming. So the framework is as follows. So here, in the first stage, we represent the continuous variables as x and binary variables as y. And then after you determine the first stage decisions, you take an expectation over a probability distribution, P, right? And then once the theta parameter is realized in this distribution, you take the corresponding second stage decisions represented by Z. And then you minimize the second stage. And then constraints have to be specified for all the parameter theta in this set, capital theta. So for different subclasses of this problem, we have done different works. The first class where we have mixed binary Z and convex nonlinear functions F and G, and the distribution is discrete. And then in the second part of the work, we deal with non-convex nonlinear functions. And in the last part, we consider continuous Z, non-convex nonlinear G and F, and continuous probability distribution. For the first three papers, we use generalized Bender's decomposition. And the last work, we use the outer approximation algorithm. But I don't have time to go to the details of any of this. So I will only talk a little bit about this paper where we have non-convex nonlinear G and F and discrete distributions P, right? But if you are interested, we can talk offline about others as well. So let me start. Let me first define the problem we have. Here, you can see X represent the first stage decisions and Y omega represent the second stage decisions. And in this case, we assume we can have non-convex nonlinear constraints. And then, and both of those variables can be mixed binary variables. Some of the assumptions here, we assume we have relatively complete recourse. The idea is that any solution X that satisfies the first stage constraints will also be able to find a feasible solution in the second stage. And the assumption too is that we assume the region is compact and the bounds of the X and Y variables are finite. Then I will first give an overview of the algorithm we proposed, then I will go to the details, right? So at high level, we are doing a spatial branch and bound algorithm on the first stage variables. Then at lower level, then we will solve each node in the branch and bound by the generalized Bender's like decomposition algorithm with some cutting planes. And there are two types of valid inequalities we add in the master problem. The first is called Lagrangean cuts. The idea is to combine with Lagrangean decomposition. The second is Bender's cut. As I mentioned before, we will convexify the subproblem with some cutting planes. All right, so here's a very high level idea of how we come up with the Lagrangean cuts. Suppose you ran Bender's decomposition and Lagrangean decomposition in parallel, right? And then what we can prove is that this type of cutting planes is valid for the Bender's master problem. So essentially here, the first term here is the objective value of your Lagrangean subproblem, which is solved for optimality. And mu is your Lagrangean multiplier at iteration k. So what we do is we add these cuts to the Bender's master problem. And some of the properties we can show is that first, this cut is valid for the master problem. And the second is that if we add these cuts in the master problem, then it is able to get a bound that is at least as tight as you were to use Lagrangean decomposition. And the second type of cuts at very high level, we call it Bender's cuts. Supposedly you are solving this Bender's subproblem. Because you have some non-convex constraints, then you cannot derive a valid cut. What you can do is we have a convex relaxation of the non-convex constraints, but the problem is still non-convex because you still have some integer variables in the second stage. And to convexify those, you can add some standard cutting planes like Gormley cuts or lift and project cuts, you name it. Now the subproblem is continuous and convex, then you can derive a valid cut and add it to your master problem. Yeah, to give you some intuition how this works. For example, if you have a nonlinear function like this, or what we can do is to derive a convex relaxation of a non-convex function. And then if you have some integer variables like y equal to either 1 or 0, then what we implemented is some rank 1 lift and project cut. So this disjunction here, basically, you include all the constraints. And then you have your variables y either equal to 1 or 0. From this disjunction, you can derive a cutting planes. For example, when you solve the relaxation, it is this point here. And then after you add the constraints, after you add the cutting plane, you can cut off this point, just some high level intuition here. And then with that, we have two types of cutting planes in the master problem, both Lagrangian cuts and Bender's cuts. But the thing is that even with these two types of cutting planes, we are not guaranteed to solve the problem to global optimum. But we still need to do some spatial branch and bound on the first stage variables. So here you can see we only branch on the first stage variable, so it scales with the number of scenarios. You do not need to explicitly branch on the second stage variables. Yeah, so let's assume this is a node at a given node Q. Then we will solve this problem by a decomposition algorithm, which is the algorithm I just described, a generalized Bender's decomposition with Lagrangian cuts. So for branch and bound, you need to specify some node selection rules, right? So here we will always select a node with the tightest lower bound. And you need to specify some branching rule. One of the branching rule that we use is to pick the first stage variables that has the largest relative diameter. It's like you pick the variable with the largest interval size, then you kind of bisect it, right? So you can imagine in the limit, all the intervals is going to decrease because you always select the largest interval, right? Yeah, so here's the overview of the algorithm. You have at high level, we have a spatial branch and bound on the first stage variables. Then once you select the node, you solve it by the decomposition algorithm on the right with the Lagrangian subproblems and the Bender's iteration. And then you have some upper bound procedure to obtain a feasible solution. I'm not going to the details of this. Yeah, and then you can prove that it actually converges to the global optimal. This is some standard proof for spatial branch and bound algorithm. Looks tricky, but what they have done in this classical textbook by Haas and Thiel is that they prove that the process satisfies the 4 lemmas. Then from these 4 lemmas, they get the theorem. So if you have a new spatial branch and bound algorithm, what you need to show is that this spatial branch and bound satisfy the property of the 4 lemmas. Then you can use their proof to prove this theorem. Yeah, so I'm not going to the technical details. You can see the algorithm is exhaustive, bounding proving, and deletion by infeasibility is certain in the limit. But yeah. So here's an application we solve using our algorithm. This is a very classical application in the petrochemical industry, which is called the pooling problem. It has been used in petrochemical refining, wastewater treatment, and natural gas network design. So here, it's essentially a network flow problem. What you get is some materials from your upstream process, like different crude oil, and then you mix the crude oil in the blenders, and then you split them and produce different products. You can imagine those as your jet fuel, diesel, and gasoline, right? In pooling problem, those are called feeds, pools, products, respectively. The idea is that we want to mix the feeds with different qualities. Your crude oil may have different compositions, right, in the pools, and then to satisfy the quality specifications and the demands of your products. The thing is that this problem is non-convex because it has some bilinear term x times y in the formulation. Yeah, essentially because you are mixing them and then you you need to model the qualities of these of different products, right? So if you model it using two-stage stochastic programming framework, the first stage decisions are some design decisions. For example, you want to choose a subset of feeds and pulls to build them, and then you decide their capacity, right? Those are your investment decisions on your initial tongues, let's say. And then in the second stage, when the customer demand arrives, you decide how to operate those product tongues, right? So for example, you need to select different contracts. You buy your feeds and the amount of feeds you purchase under different contract and the mass flow rate and so forth, right? And the constraints would include the mass balance and the quality specification on which contract you select. So this is a two-stage stochastic programming problem with non-convex nonlinear constraints. And we assume different sources of uncertainty in this, including the demand of your products, the price of the feeds, and the selling price of your products. So here is the size of the problem we solve. We have 9 binary variables, 9 continuous variables in stage 1. And in stage 2, we have 32 binary variables per scenario and 22 nonlinear constraints per scenario in stage 2. If you just use the commercial solvers like Barry, ANTIGONE, and SCIP to solve this type of problem, they run out of 10,000 seconds time limit and still cannot close the optimality gap. But if you use the proposed decomposition algorithm, what is shown here is that the first row here is the time and the optimality gap. The second row here is the number of nodes you need to solve. So if you use generalized vendor decomposition with cutting planes and Lagrangean cuts, it can solve the problem in one node and close the optimality gap. So it closes the optimality gap at the root node. But if you disable some of the features, for example, disable the cuts or disable the vendor's part, then it performs a little bit worse, right? That's this part. So I want to talk, how many constraints? The scenarios are 27 scenarios. So here's the number of scenarios. Yeah.
And by then I think
yeah, Groovy cannot solve MIQCP at that time.
Oh, yeah.
Okay. I will finish up with some other research I did, but if you are interested in the details, we can talk offline. So this is power system applications. What we want to decide is some how many generators you need to install in Texas. And we solve it with a mixed integer linear programming model. And this is an application in shale gas in collaboration with a company at Pittsburgh. So what they want to decide is how does the uncertainty in natural gas price affect your business? So what this company do is they try to drill some wells in a well pack. And the last one is a deep reinforcement learning algorithm for some chemical scheduling problem. Basically, we use a deep reinforcement learning agent to solve a scheduling problem here. So that's it. And my time is up, and here's some of my collaborators. And with that, thank you for your attention. I'm happy to take any questions.
What do you do when you pick the first variable and then after that the second parameter
not the feasibility, right? So in this case, we did not deal with feasibility explicitly. We assume relatively complete recourse because once you have the constraints in the master problem, you guarantee each scenario is feasible. But in order to handle feasibility, that might be a little bit tricky when it's non-convex. My hypothesis is that with the Lagrangean type of framework, you can prove a node by infeasibility, but we did not do that. Yeah, we did not do that explicitly. But I think we can prove that Lagrangean cuts is tight in some sense to prove the node by infeasibility. Yeah.
Very quickly, can you improve talking about
yeah.
Can you go back to
Yeah, sure. Maybe it's easier if you get that. Yeah. Oh, strongly consistent is pretty much like when the bound shrink to 0, then you get the true optimal.
Okay.
Yeah.
Yeah. So it's very interesting how what stochastic programming is very connected to dynamic programming, for instance.
Right.
What we were saying at the beginning, the linear program, realize it, for this.
Yeah.
Then maybe it doesn't happen with some context.
Right. Yeah.
It's very interesting. I don't know anything about stochastic programming. Usually on by level you do exactly this kind of.
Okay. Yeah.
But I was wondering, so in the non-convex case, what happens is that we get a non-convex second level feasible set. Right. And then you separate inequalities that are valid for the convexification of this set. Right. So you said that you have to have spatial branching bounds to make the full algorithm converge. Yeah. Why that? Are cutting things sufficient in this case, or? Okay, I see. Yeah. Right. Yeah. That's actually a good point. So in the non-convex case, the cutting planes are not sufficient because theoretically you cannot get the convex hull of a any non-convex set. But if you you know how to get the convex hull of a non-convex set, let's say in the linear case, right? You can prove you get the convex hull, then the cutting planes are sufficient in a Bender's framework. But in the non-convex case, because the tools we have are not sufficient to get the convex hull, so we need this Lagrangean type of framework to converge. Yeah. But I mean, if you don't have this, but then also you can have a convergence algorithm. Just speed up your spatial branches.
Yeah, exactly. Yeah. That's a very good point. You essentially get the idea. Yeah.
But without the spatial. Yeah, no, because we want to explore the whole space of the decision variables, and you may not see the whole space unless you see it in a certain way. So this is how I think to use the spatial branch to see the whole space of the decision variables. Yeah,
that's exactly the idea. Yeah.
We have just one question, one last question from Jeff from Zoom that asks, can you already solve your pooling problem?
Yeah, now with the current version of Groovy, it is able to do that. But when we were publishing this paper, was not able to do that. Yeah.
Okay. Thank you, Sam.